everyone, thank you so much for clicking onto the video. Today's learning objectives are to know that alkenes are unsaturated hydrocarbons containing a carbon-carbon double bond comprising a pi bond and a sigma bond, and how there's restricted rotation of the pi bond. And then we're going to explain the trigonal planar shape and bond angle around each carbon in the carbon-carbon double bond of alkenes in terms of electron pair repulsion. So now we're going to talk about alkenes. So alkenes are a homologous series that have the general formula CnH2n. But one really important thing to note is that alkenes have this carbon-carbon double bond. And in order to have a carbon-carbon double bond, we need at least two carbons. And that means that in this general formula, N has to be bigger than or equal to 2. So our first alkene will be ethene. And ethene's formula would be C2H4. Another thing about alkenes is that they're unsaturated hydrocarbons, and this is because they have carbon-carbon double bonds. Alkenes will burn in oxygen completely to produce carbon dioxide and water, and they will also burn in a limited supply of oxygen, so incomplete combustion, and that would produce carbon monoxide or carbon. And alkenes will also react with halogens, hydrogen halides, concentrated sulfuric acid, and water. Alkenes are also produced on a large scale when crude oil is thermally cracked. And they are much more reactive than alkanes, and this is due to their carbon-carbon double bond, and so they're really good starting materials to manufacture other chemicals. Ethene is especially important in the manufacture of polymers such as PVC, polyethylene, and also polystyrene. Now we're going to talk about the structure of alkenes. So ethene, which is the first alkene we have, has the formula C2H4, and it is a planar molecule, meaning that it's flat, and the angles between the bonds are roughly 120 degrees. The double bond exists as a sigma bond and a pi bond, and the p orbitals on each carbon atom overlap to form this pi bond. The electron density of the pi bond exists above and below the plane of the molecule, and the presence of this bond prevents the rotation about this double bond. So the diagram we have at the bottom is basically what the double bond consists of. So we have the normal sigma bond that we have in carbon-carbon single bonds, but now we have these p orbitals on each carbon atom which have overlapped to form this pi bond. So one pi bond involves the two electrons moving above and below the plane of the molecule, and it's this bond that prevents rotation about a double bond, compared to how we can have rotation about a carbon-carbon single bond because that's just a sigma bond.